Hi, welcome to a lecture on how to design a stepped impedance filter. First, let me emphasize that this lecture assumes that you have seen a previous lecture, and this previous lecture is entitled Equivalent Circuit for a Lossless Electrically Short Transmission Line. If you haven't seen this video yet, I'll leave a link in the description, but please do see that video before you go through this material, because I will have already defined some terms and concepts in that previous lecture. So let's get started. A stepped impedance low-pass filter is a filter which is comprised of a continuous section of transmission line in which we change the impedance of the transmission line in steps. Each one of these sections of the transmission line represent a shunt capacitance or a series inductance. And so what we can do is we can develop a prototype filter comprised of discrete inductors and capacitors. And if we have such a filter ready to go, then we can transform that discrete component prototype into one of these stepped impedance low-pass filters. So what we're going to do here is go through the mechanics, the specific procedure that you would use to do this transformation. There's a couple things we need to be clear on before we get started with the design, because they become important at various points in the process. One is that this scheme requires that each section of the design has to have a length that's much, much less than half a wavelength. But then the question comes up, of course, what wavelength? In other words, for what frequency does this have to be true? Well, ideally, we would like this to be true for frequencies as large as possible. And then we would make sure that this constraint of being electrically short would be true even for the largest frequencies. But in practice, we're going to be designing low-pass filters. And the response in the high-frequency part of the low-pass filter is really not that important. Typically, you want some specific feature in the pass band, and what's happening in the stop band really isn't so important, just as long as it's actually a stop band. So in practice, what we do is we choose this wavelength at which we will enforce the criterion of electrical shortness to be at a frequency equal to the cutoff frequency of the filter. That is, at the 3 dB point in the low-pass response of the filter. So with that in mind, we will enforce this criterion with respect to a wavelength, which we will call lambda sub CO, CO for cutoff, which is equal to the phase velocity divided by the cutoff frequency. So to restate the actual requirement now, when we mean electrically short, we now mean that each one of the line segments should be much, much less than the wavelength of the cutoff frequency divided by 2. Now, that's not the only requirement we have to meet. In order for all that transmission line magic to work, we had two other requirements, and they had to do with the values of the characteristic impedances for each of the segments. Here we're going to define two values, Z0L and Z0H. And these will be the two values that we will use for the segments. In other words, we'll have segments which alternate in characteristic impedance between this value Z0L and Z0H. Now, from that previous video, the requirement that applies is that Z0L be much, much less than 2 over beta sub CO, L sub n, times the characteristic impedance at the ends of the filter. And this has to be true for each segment. That's why I say here all n, where n indexes the segments. This beta sub CO is simply the phase propagation constant at the cutoff frequency. So that would be omega at the cutoff frequency divided by phase velocity, or 2 pi times the cutoff frequency divided by the phase velocity. And similarly, we require the high value of the characteristic impedance, Z0H, to be much, much greater than beta sub CO times the length of segment n times the characteristic impedance at the input and output for all the segments. So basically 3 requirements we have to meet. Each segment has to be electrically short, and also the 2 values that we choose to alternate between in the scheme, they have to be sufficiently low and sufficiently high, respectively. Now, those requirements don't tell you how to select Z0L and Z0H. So how do you choose them? Well, generally, you want to make Z0L as small as practically possible, because that will help you meet this requirement. And similarly, you want to make Z0H as large as practically possible, again, because it will help you meet this requirement. But the question is, what's reasonable? Well, that depends. If we're doing this in microstrip, and typically we would be, just imagine what the geometry of these segments looks like. When Z0L is small, that means we have a wide strip, right? A wide microstrip gives us a small characteristic impedance. So if the geometry of the metallization looks something like this, we're probably okay. If we continue to try to make that characteristic impedance smaller, then the strip is going to become wider. And at some point, it's going to start to look like a stub. So at some point, we make Z0L so small that electromagnetically, it's not really clear whether this is a section of transmission line that just happens to be wide, or whether, in fact, it's a stub. And the waves don't know what your intent is, so it's up to you to try to avoid this situation. So if you find this situation happening, you have to increase that small value of the characteristic impedance. Now, the problem with that is that might cause you to violate the electrically short requirement. Well, in this case, now you've got a tougher design problem. You might have to do some kind of EM simulation to figure out what you can get away with. For Z0H, that's something we want to have a large characteristic impedance. That means a narrow strip. Well, in principle, there's no limitation on how narrow you can make a strip, but if you're going to manufacture it, there may be a minimum width. If you make the width too small, it might be too hard to ensure continuous metallization, and you might get breaks, for example. So the limitation here will be something probably pertaining to manufacturability. It would be something you'd read off the spec that's provided by your PCB manufacturer. With that in mind, here is the design procedure. First, let's consider what the givens are. Going into this process, you're going to have a worked out LC low-pass filter, right? You've already got some filter that's comprised of discrete capacitors and inductors. It's low-pass in the way I just showed you earlier in this video. It's got a known input-output impedance, and we're going to call that Z0, and that's also going to be the characteristic impedance of the transmission line at the input and output of the final design. And we're going to know its cutoff frequency. If you don't know how to design such a filter, there's a video, I will link to that from the description, which explains how to design such filters. The 2 other things you'll need, of course, are Z0L and Z0 high. I just told you that there's no specific way to choose these things. There's only considerations to keep in mind here. And if you have no other basis to choose, I would suggest something like making Z0L something like 1/3 of Z0 for the initial try. So for example, if the input-output impedances are 50 ohms, maybe make this 50 divided by 3. And similarly, maybe make Z0H something like 150 ohms for Z0 equals 50 ohms. And if you find the design is unsatisfactory, then you can fiddle with these numbers. And then the 4th thing you'll need is the phase velocity. Now, the phase velocity depends on the dielectric constant of the PCB material, assuming you're doing a microstrip implementation. This usually, not always, but usually does not vary significantly with frequency. All right, so the procedure goes like this. We're going to need to know the wavelength at the cutoff frequency. As mentioned before, that's the phase velocity divided by the cutoff frequency. And we're going to need to know the phase propagation constant at the cutoff frequency. That's just 2 pi over wavelength, or in this case, 2 pi over the wavelength at the cutoff frequency. From this point, the procedure is very simple. The length of the first line you choose to be Z naught L times phase velocity times C1, the capacitance of that first capacitor. This equation comes from considerations in that earlier video. As soon as you calculate that length, you want to immediately check and make sure it meets the requirements. So make sure that L1 is much, much less than lambda sub CO divided by 2, and also make sure that 2 times Z naught divided by beta sub CO times L1 is much, much greater than the value you selected for Z naught L. All right, both those requirements have to be true, or you'll be violating the approximations that led to this equation in the first place. For the second segment, that's going to be simulating an inductor. And so the length will be given by this expression, phase velocity times the inductance of that second inductor divided by Z naught H. And again, you want to check and make sure that length meets the requirements, specifically that L2 is much, much less than the wavelength of the cutoff frequency divided by 2. And also that beta cutoff, the line length times Z naught is much, much less than Z naught H. So once you see this for those first two segments, it works exactly in the same way for all remaining transmission line segments. The only thing that changes here is subscripts. Now, for microstrip implementations, you would set the segment widths such that the characteristic impedance of that segment is the right value. And that's just setting the width. There will only be two widths, one width corresponding to Z naught L and the other width corresponding to Z naught H. And you're done. Of course, you should check your work, and I'll show you how you can check your work when we do the example. So, here's an example. I'm coming into this problem with a worked out design for a Butterworth low-pass filter. The cutoff frequency for this filter is 1 gigahertz. The input and output impedances are 50 ohms. And in order to achieve this response then, here are the component values, C1, L2, C3, L4, and this is symmetrical design. So C5 is equal to C3, L6 is equal to L2, and C7 is equal to C1. The nice thing about symmetrical designs here is that you only have to work out details for 4 segments, and then the other 3 will be determined by the first 3 of those 4 that you worked out. I'll choose Z naught L to be 20 ohms. This is an arbitrary choice here. In this case, that's Z naught divided by 2.5. I suggested Z naught divided by 3. Again, I'm trying to make the point that there's no magic value here. I'm just using this to get started. Perhaps in the real example, or in a real life example, perhaps I already have information about 20 ohm transmission lines, and that's close enough here. I might as well use it. Z naught H, I'm going to choose to be 120 ohms. That's 2.4 times Z naught, not 3 times Z naught. Once again, just trying to demonstrate that there's nothing magical about choosing these values. So to summarize here, Z naught L and Z naught H, that would be based on PCB material selection and perhaps lucky guesses or perhaps experience. The fourth thing we need is a phase velocity. Here I'll say it's simply 0.6 times c, c being 3 times 10 to the 8th meters per second, the speed of electromagnetic radiation in free space. Or you could equivalently think of this as being a velocity factor of 60%. Right, so the phase velocity would be determined by the dielectric constant of the material you use in the printed circuit board. So there are the givens. So now we begin the procedure. First, we determine the wavelength at the cutoff frequency. That, following the formula, is 180 millimeters. Then we determine the phase propagation constant at the cutoff frequency. That's 34.9 radians per meter. So we have those values ready to go when we need them. Now we calculate the line lengths. L1, given by this expression, we have all 3 of those values. We find 5.1 millimeter. We immediately want to check and make sure this is true. Well, 5.1 millimeters is certainly much, much less than 90 millimeters. So we have met the electrically short requirement. And similarly, when we check it against this requirement, we find that expression gives us 560 ohms, and that's much, much greater than 20 ohms. So that requirement is also met. So it looks like this is good to go. For the second segment, we have this expression to compute. That gives us 14.9 millimeters. 14.9 millimeters is certainly much, much less than 90 millimeters. And we also check that our characteristic impedances are okay. In this case, we find 26 ohms. That has to be much, much less than 120 ohms. We're good to go here. So now we're just repeating that process. We only need to do it 2 more times. We get L3 is 20.7 millimeters. That's certainly much, much less than 90 millimeters. And this value of 138.6 ohms is certainly much, much greater than 20 ohms. For L4, we get 23.8 millimeters. That's still much less than 90 millimeters. And the impedance criterion, we get 41.6 ohms. That has to be less than 120 ohms. Here you can see we're starting to get close to violating this approximation, right? 41.6 ohms is about a third of 120 ohms. Factor of 3, is that much, much less? Not certain, but we can try it and see what happens. I'll tell you in this case, it's good enough. From the symmetry of the filter, we know that L5 is equal to L3, L6 is equal to L2, and L7 is equal to L1. So no need to recompute those. All that's left to do is to check it and implement it and possibly measure it. Let's talk about how we check this design. This looks complicated, but it's really the same simple procedure applied, in this case, 7 times. So just bear with me here and see what's going on. If I had just this section of the filter, just that last section, and into the output here, which has a characteristic impedance of Z0, I could calculate the input impedance of just that much. I'll call that Z sub 7. Z sub 7 is a function of frequency. It's a function of frequency because the electrical length varies with frequency. But we know the input impedance of such a thing. This is simply a transmission line terminated into some impedance. That expression is it's very simple. It's simply the characteristic impedance of that section of transmission line, and then this kind of goofy expression where you have this constant, which I'm calling gamma sub 7, and this thing which describes the phase of the standing wave on the transmission line. This is quite simple to compute. Gamma sub 7, this thing I've defined here, is given in the normal way, the way that you normally use to compute a reflection coefficient. The characteristic impedance you're going to minus the characteristic impedance that you're coming from, and then the same thing with a plus sign in the denominator. And here beta, the thing that appears here, is the actual phase propagation constant, which is a function of frequency. Not the phase propagation constant at the cutoff frequency, but rather the actual phase propagation constant at the frequency that you're actually considering. And that is 2 pi f divided by phase velocity. So you have everything you need to get Z7, the input impedance into that last segment. Well, now you back up one step. The input impedance looking in to the input of the next to last section, we'll call that Z sub 6. The procedure is entirely the same, only the subscripts change. So now we have a reflection coefficient gamma sub 6, not gamma sub 7. That is a function of frequency now. It's a function of frequency because the impedance that we're going to is Z sub 7, the thing we computed here, and the characteristic impedance we're coming from is Z0 H, which is this characteristic impedance. So the expression is same, beta is the same. We now have a value for that input impedance, which is frequency dependent. And now we just iterate this for each new segment moving from right to left. So when we get to the first segment, that's Z1, which is a function of frequency. Gamma 1 is Z2F minus the characteristic impedance of that section of transmission line. Same expressions otherwise. So now we have the impedance looking into the entire structure. In other words, the input impedance of this filter when it's terminated into Z0. So what are we going to do with that? Well, if we know that input impedance, then we can calculate a reflection coefficient, which is associated with that impedance. The voltage reflection coefficient at the input of that filter is simply Z1, function of frequency, minus Z0, because that's the characteristic impedance that we are coming from. And in the denominator, Z1 plus Z0. That's the voltage reflection coefficient at the input to the filter. Well, now what? Well, now we can get the transducer power gain, which is a function of frequency. The transducer power gain is, as always, the power delivered to the output relative to the power available from a conjugate matched source. Well, in this case, that's simply 1 minus the power which is reflected. And the power which is reflected is the magnitude of gamma in squared. Because any power which is not transmitted into the filter is reflected. So if I calculate the power which is reflected and subtract that from 1, I've got the fraction of power which was transmitted into the filter. And since the filter is, at least in principle, lossless, all the power which makes it into the filter also makes it out the output of the filter. So this is a very straightforward way to calculate the response of this filter. In fact, if I do this right, and I've done the design right, the TPG I calculate using this method should be very close to the transducer power gain, that is the frequency response, of the prototype filter, the discrete LC filter that I started with. It will not be exactly the same. And the reason it can't be exactly the same is because in order to get to this stepped impedance approach to design, I had to make some approximations. Those approximations are justified. I confirmed that they were justified when I did the design, right? That's what all this stuff was about. Nevertheless, that simply means the approximations are valid. It doesn't mean I have exact equivalence. So I do not expect that even once I do this, I'm going to be exactly the same as the original prototype. I can only hope that I'm pretty close. So in the example that I worked out up here, I have done this check and plotted the results. And here's what I find. This is transducer power gain as a function of frequency. Recall that the cutoff frequency is 1 gigahertz. And 0 dB is lossless response, so the passband is flat. Blue represents the discrete LC prototype, so that blue curve is the Butterworth response. The red curve is the response that I've calculated for the stepped impedance filter. So what you see is that in the passband, this stepped impedance filter performs wonderfully. It is also at least approximately flat and has a cutoff right around 1 gigahertz as we intended. Not exactly the same, but then again, we didn't expect it to be exactly the same. We just expected it to be close. And in the stop band, the fall off is similar, but ultimately diverges a bit from the prototype. Again, we expect this because of the approximations we had to make to use this design procedure. But overall, this is a win, right? What we've managed to do is come up with a stepped impedance filter, a single continuous section of transmission line, which is able to closely emulate the behavior of the discrete LC prototype filter. As a final note, I'll just mention that the microstrip implementation of this filter would look something like this. Right, a single continuous section of transmission line. Here is the transmission line at the input and the output of the filter. The first section would be relatively wide, having length L1. The second section would be relatively narrow, having length L2, and so on. And I've tried to draw this roughly to scale, but it's not precisely to scale. Nevertheless, it gives you a good idea of what this filter would end up looking like. That concludes this lecture on how to design a stepped impedance filter.